Alrighty, 1.5, atomic structure and electron configuration. So let's focus on some Gen Chem review about the atomic structure and how it's not quite as accurate as what we've talked about previously if you have taken general chemistry. So we have two parts of the atom. So we have the nucleus, which is the protons and the neutrons in the middle, and then we have the electrons on the very outside. And so that's just how it is. We also learned about the electrons are in shells, aka the Bohr model. So in this example here for aluminum, we have the electrons that are on the outside on these separate rings. Those rings are shells. They're also known as energy levels. And so Bohr's model, we learned something called the octet rule, which is the first energy level, so the one over here, as I'm indicating with my mouse, is going to hold a maximum of 2 electrons. In the second energy level, we can hold a maximum of 8. And in that third energy level, we can hold a maximum of 8. So it's the octet rule, aka the 2-8-8 rule. The valence electrons are the outermost electrons. The core electrons are the inside electrons. So for this example here, our valence electrons are going to be the ones on this third ring on the outside, and we have 1, 2, 3 valence electrons according to this diagram. The core electrons is everything else underneath, so we have the second and first ring. Those are the core electrons. Mass number, in case you forgot, is protons plus neutrons, because all of the mass of an atom is pretty much concentrated in that nucleus. Electrons do have like a tiny, tiny bit of mass, but it's so negligible that we consider it 0. And then the charge is protons minus electrons. So if I have more protons, we're going to be a positive charge. If we have more electrons, it's going to be a negative charge. If we have the same amount, it's going to be a neutral charge. Okay, so the Aufbau hotel analogy, aka the Aufbau's principle, is an analogy based off a hotel. It makes it a little easier to understand. It is useful for a variety of reasons, and so I'm going to talk about this in terms of like hotel rooms and stuff. It'll be a lot easier. The Bohr model, like this aluminum that is here, it works for some purposes, but not all purposes. And so the Aufbau model is, more makes sense in terms of giving more precise locations of the electrons, because the Bohr model, it says, oh yeah, we're in like the second energy level or the third energy level, but it doesn't give more information. And so this hotel analogy that I'm going to do explains a lot more. So first I'm going to talk about this floor plan, okay? So the Aufbau hotel, as you can see in this like diagram here, it's a hotel that's built up, like kind of in a weird vertical way where the first floor only has a certain amount, and then the second floor has more, and then you get more and more rooms and different kinds of rooms as you go through more and more floors. So here I have the first floor, the second floor, and the third and fourth floor, and I could have a fifth and a sixth floor if I wanted to. And so in the first floor here, we have one room. It's called the suite. And I'm just going to add a circle. Great. In the second floor, I have 2 rooms. So again, this is S for suite. I have the P room, which is going to be the penthouse room. And so I have 1 suite room in the second floor and 3 penthouse rooms. On the third floor, I have 3 types of rooms. I have suites, I have penthouses, and I can have like deluxe rooms, or just letter D. And so in just like the same pattern we've been finding, the S, there's going to be 1. P is going to have 3 rooms. And then the deluxe room, there's also a pattern to the amount. I could do it based off odd numbers. So 1, 3, 5. And then the fourth floor, I'm going to have the other room, which is F. I could call it fantastic rooms, I guess. And so I have 1 S room, 3 P rooms, 5 D rooms, and then I will have 7 7 rooms for the F. These rooms are called orbitals for actual atom purposes, and electrons will always want to double up in these rooms, which I'll talk about in a few moments. So here's how it looks like in a better format. And so like I said, rooms are always going to be doubles. You can always fit 2 electrons per room. Now, sometimes some rooms will be empty, sometimes rooms will be only half filled, but again, I'll talk about that in a few moments. Okay, so despite having these different types of rooms, they also cost different amounts. So the cost or price schedule for these rooms are shown here. As I go up the different floors and the different types of rooms, you increase the cost of the room. So the higher you are in terms of how this particular price schedule is set, the higher the cost. So that first room in the 1S doesn't cost that much. The 2S costs more, but whatever. And then the 2P cost a little bit more, which is why you could see it's staggered this way. And so 3S and 3P is the same way. And then the letter D rooms are going to cost way more compared to the 3P, which is why it's up here. Now you can see here 4S is going to cost more than 3, in general 3S and 3P, but the 3D again costs a lot, which is why it's up here, and then 4P will cost a little bit more. And so that kind of patterning will continue on as you continue adding more and different types of rooms. So again, the energy or the cost price is going to increase as I go up. Cool. And so the way that electrons want to spend money at this hotel is they want to spend the least amount. They always are going to go for the lowest price room first, and then they will double up as needed, and then, so on and so forth. So, if they're reaching, the different kinds of rooms and they start doubling up, this is something called the Hun's rule. And so if it's different rooms but the same price, so for example, 2P here, I have 3 different rooms, but they're all the same price, they're all going to fill in singly first. After they fill out singly, they still don't want to go to 3S because it's still expensive, so then they'll start doubling up and keep putting an electron here, an electron in here, and here until I go to the 3S. Now, if you're like, what the heck is she talking about? I can explain with some examples. So I'm going to use the periodic table down here just to emphasize how many electrons. All of my examples I'm going to assume are neutral. I'll go over some examples that are charged in a moment. And so we're going to start with good old helium. Hydrogen. So hydrogen has 1 electron. And so in terms of the electrons filling out the price schedule point, it's going to be 1. And so I would draw a 1 like so. If I was at helium, I have 2 electrons. Now, I could theoretically have the electron here, right? However, this costs too much. And so electrons would rather double up. And so in this case, it's going to be 1s, and then it's going to be drawn in this way. And so then I can keep going. So lithium is 3 electrons. And so in this case, the next cost-efficient way would be here. And then if I go to beryllium, then it's going to go here. And then if I go to boron over here is going to be 5 electrons total. So it's 1, 2, 3, 4, add a 5th one here. If I keep going where carbon is 6, again, I do not want to double up yet. I would rather fill in the rooms first before doubling up. So carbon would be over here, the other electron, and then nitrogen. And then if I kept going, this would be oxygens, this would be fluorines, and this would be neons. If I keep on going, sodium would have a total of 11, so this would be 11. I can always double check by counting 2, 4, 6, 8, 10, 11. And then magnesium would be 12, and then aluminum would be 13. So it's always going to go based off the price. Because, if you notice here, I don't necessarily will fill out the same way here. For example, if I keep going into the 3Ds, I can fill out 3D, but I want to fill out 4S first because it'll be a little cheaper compared to 3D. So even though 3D there is, again, rooms in the 3D space, 4s cost is cheaper compared to the 3D, so the 4s will fill up first before the 3D. The price will always be the supreme choice for these electrons. So the cost or the price that I was talking about actually corresponds to energy. So the electrons want to use the least amount of energy in order to fill out this map. And so this is called an orbital map. And so they're going to try to fill out the, again, least amount of energy. So you can see here it's increasing as I go up. The F's and the D's are a little weird, not gonna lie, especially for F, but we don't really deal with that much, so I'm not gonna really focus on that. All right, so these rooms, we can draw them in different ways. It just depends on you. So earlier we had them as circles over here, but you can also use squares or just simple lines. Again, it's really up to you. When I do these examples, I generally stick to lines just because I'm too lazy to draw a circle and a square, but you do you. If I wanted to do 3D with 7 electrons in it, there are 2 ways to draw it. So earlier you saw me draw, let's go back, with these kind of half arrow things. And so I'm going to do those half the arrow things again. And so if this was the 3D area, I'd go 1, 2, 3, 4, 5, 6, 7. There is another way to do it called the slash way. So the slash way would go 1, 2, 3, 4, 5, 6, 7. So again, it's another way of doing it. The most common way is the half arrow way here, but the slash way works as well. The AP test would take both. I'm personally going to use the half arrow way because that's what you're going to see more in college if you need to use this anymore besides in general chemistry. But again, you could do the slash way too. It's the same thing. So econfig, or electron configuration, can be written as such. So the first number, which is a big number, is the energy level that is corresponding to the floor that I was talking about earlier. So if I go back here, we have the different floors, right? And so that's what that big number corresponds to. The S is the type of orbital, and so in that case it was the type of room in my analogy, and then how many electrons are chilling in that orbital, or how many electrons are chilling in that room. So that would be the superscript. And so I'll do a quick example here. We're going to go ahead and do bromine. And so when you see bromine here, you can see it's going to be in the 4p. You can also see the electron configuration follows a pattern on the periodic table. You can see we start at 1s, and then this is the P block, so we start at 2P. This is the D block where we start at 3D, and this is the F block where we start at 4F. And so you can follow that pattern as you do, because that's what I do. And so I'm going to go ahead and do bromine as an example. So I'm going to use that orbital diagram, except a colorful one, same thing though. And I'm going to go ahead and start filling this in. So, we have however many electrons this is, whatever. I have my 1s filled with 2. I then have 2s is going to be filled. So let me just cross out what we're doing. So 2s, that's over here. And then I have my 2p, so that's over here. So 1, 2, 3, 4, 5, 6, because I count across 6. Notice that I drew that where I filled up each room first and then started doubling up. It's a good habit to do so you don't make the mistake of accidentally doubling up instead of and having like an empty room or something. So I recommend doing that. Then 3s we have 2, so 1, 2. And then 3p we have 6, so I go 1, 2, 3, 4, 5, 6. And then 4s I have 2, so I go 1, 2. And then 3d I have 10 if I count across this. And so I accidentally went into the P block. So there, I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then bromine, we have 5 total because I just count 1, 2, 3, 4, 5. And so in the P block, I'm going to fill up first singly 1, 2, 3, and then 4, 5. So that's how I fill out that orbital diagram. And so If I want to write the ground state electron configuration, that's writing the whole bloody thing. So you start off with 1s, or I'll just start look at down here in my little thingy. So 1s, how many are there? 2. Then I got 2s, and then how many? 2. 2p6. I'm running out of space already here. 3s2, 3p6, 4s2, 3d10, and then 4p 2, 4, 5. Cool. So that's the ground state, or the long way of writing electron configuration. There is something called the noble gas way. And so the noble gases are the very last column of the periodic table. They're, as it sounds, gases. And so you find the noble gas that you've gone through. So when looking at this, we went through helium, cool. We went through neon, cool. We went through argon, cool. We did not go to krypton. So you want to find the, highest noble gas that you've gone through without going over. So in this case, it's going to be argon. So to write the noble gas way, you put it in square brackets, write A, R, square bracket, and then you continue to the next line on the PT. So that's going to be 4s. And so in 4s, I filled out 2. In 3D, I filled out 10. And then in the 4p, I filled out 5. So you need to be able to draw these orbital diagrams. You need to be able to write down electron configuration in the ground state and the noble gas way. If the AP test does not tell you a specific way of writing electron configuration, pick whichever you want. So if it's an FRQ and it doesn't say ground state or noble gas, pick the one you like. Cool. So go ahead and try this out. You're going to try to do the orbital diagram for calcium, and then you're going to write the ground state and the noble gas electron configuration. So go ahead and pause this video, and then I will show the answer in a few moments. Alrighty, so here's calcium, where calcium is at the 4s zone, and we're filling it up to 2. So here it is filled up. I just picked a random screenshot I found. Notice that it can also be written like this. I will say, though, the AP test prefers it to be staggered like this because they want to see you understand the energy level increases as you go up, rather than putting it in one line. So I would recommend writing it this way. I haven't seen any notes about this being accepted, so just assume it's this way. And then for ground state, you just go through every single, floor and room that you're going through. So there it is. And then noble gas-wise, we went through argon as the latest one possible, and so you only need to put 4s2. Cool. Alrighty. Iron. So iron is funky for a variety of reasons. First, let's go ahead and just fill out the thing as we do. So we have 26 total electrons, and so filling out that orbital diagram, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So if I had to write the electron config, I would just go in order from 1s2 up to 3d6. Cool. So that's cool. Now, again, let's fill this out just so you can see why you should do the orbital diagram versus just having the rooms and the energy levels, right? So, boom, bam, bam, bam. And then we got our 3s, and then our 3p. Now notice I filled out the 4s first before I went to the 3d. Because again, the cost of 4s is cheaper than 3d. So that's why you want to do the orbital diagram rather than the floor plan, because again, it's based off energy costs. Now, if I had iron as an atom, what would I bump into? Like likely, right? So let's look at the Bohr diagram version because it'll be a little easier to see. And so here we have the first energy level, second, third, fourth. As a reminder, the energy levels are these numbers here or the number in the very front of the letter. And so here I'm in the fourth, and then it is 4s. So likely I would bump into the 4s electrons because they are the valence. They are the outermost. And so in terms of what I should box, it would be this one. Or this one, whichever one you want to box to show your answer for this. But again, if you were to bump into it, you're going to bump into the valence electrons most likely. Cool. So again, be very careful about filling this in. Again, I would go based off the orbital diagram and not the floor plan, because the floor plan doesn't tell you how much things cost. Cool. Alrighty, here's another your turn. Do iodine's orbital diagram, and then do the noble gas electron configuration, and then do the ground state electron configuration for an ion. I know I haven't talked about doing ions yet, but try it out. See what you think. Go ahead and pause this video, and then I'll talk about it in a few moments. Okay, so iodine. Here's an example. I don't have much to say. It's common sense in terms of the pattern. If I go, this is 2p, 3p, 4p, 5p, so it's over here. Krypton is the lowest noble gas it goes through, so that's why you put that in brackets, and then you just go across. 5s2, 3d10, 5p5. And then here's the diagram, just one I found online. Boom. Cool. Now, I want to talk about the iron ion, because this one's going to be interesting. So, this is ground states iron, not Fe+2, so not the ion. But going back to the Bohr model of iron, we're filled up to the 4s. Now, remember, this is an ion. So, let's actually recap something from the very beginning. So, charge was P minus E. And I know my proton number because my proton number is based off the atomic number. So hydrogen has 1 proton, helium has 2, fluorine has 9, phosphorus has 15, and so iron will always have 26. The charge of this guy was positive 2. So how many electrons does this have? In this case, it has 24 electrons, because 26 minus 24 is positive 2. And so, because this again is the ground state, having 26 electrons, because we're assuming neutrality, if I have 24, you're going to get rid of the outermost electrons. So even though, this one's drawn kind of weird, but whatever. Even though we have something in 3D or whatever, you want to get rid of the valence electrons here. So that would be these guys in the Bohr diagram that I scribbled out. And then it would be the 4s2 here. And so when I'm talking about the ground state of it, it's going to be everything except no 4s. So make sure that you know that if you're removing electrons, it's generally in the valence electrons. Now, some people get confused about Hund's rule and Aufbau, where the rooms want to be filled out halfway first before you start doubling them up. And so some people might think, oh, I'm going to change this to like 3D5 and then 4S1. That way the 3D will be half filled with everybody and the 4S will be half filled. Having half filled is usually very energetically pleasing for atoms, but if they still want to remove stuff from the valence first, usually. There are some exceptions to this, though. So the weird exceptions to the transition metals, I'm not going to go over. The likelihood of the AP Chem test asking is slim, but it is not 0. And so I do have class video links under Unit 1 references that do talk about these weird exceptions. So do feel free to watch those so you would know. But again, the likelihood is slim, but not zero. And so I'm not going to go over those. Cool. So let's summarize what I said. A lot of it I said out loud, but I'm going to go ahead and summarize here. So the floors of the hotel room are going to be the shells or the energy levels. That's designated by the letter N, usually. And then the types of rooms are subshells. So the sublevels or suborbitals, those are other words for it. That's the SPDF stuff that we were talking about earlier. And then the room itself, like one single room, is an orbital. So all those circles where we were drawing the arrows, that is an orbital, okay? And then the price is the energy, like I said before. And so Hund's rule, to formalize it more, is that every room is going to be single until you run out of rooms in that energy level, or the type of room rather. And then you're going to fill them up before doubling. So you're going to fill up all the S. Well, there's only one room for S. And then for the P, you have 3 different orbitals. And so you're going to fill out each of those orbitals first before you start doubling up. So always single first before double. And then eventually when you filled up everything, you go to the next energy cost room or orbital. The Aufbau principle, like officially, in terms of definition, you're always occupying the lowest energy orbital first. So, energy cost is how I think of it. And then you might read the textbook and you might have ran into quantum numbers. And so those are NLM. You don't need to worry about it for the AP Chem test. They will become a thing in general chemistry in college if your professor uses it or not. Essentially, it's just defining like exactly which particular electron you're talking about. So if I go back to like this, for example, each of these electrons here have their own like name or story or whatever you want to call it, right? And so if I wanted to talk this one, they will have their own N, L, and M for quantum numbers. But again, that's more of a college thing and not an AP Chem thing for some reason, so you don't need to worry about it. Cool. Okay, so let's summarize what we learned, like what is even electron configuration. And so again, the Bohr model is, our nucleus that has our protons and neutrons, and then we have our energy levels here, 1, 2, 3, 4, and it can continue as usual. And so in the Bohr model, it's 1D. It's not even 2D, it's 1D, it's flat. We're seeing the electrons here and the energy levels wherever they're at. But electrons are in 3D space. And so the chance of electrons being around the nucleus are these orbital rooms. So we're drawing these rooms and these are the electrons where they're most likely going to be there. Are they always there? Not necessarily, but most of the time they're going to be in there. And so if I think of this, oxygen, as 1s2, 2s2, 2p4, there's going to be an S room that's spherical, so there's going to be 2 electrons that are going to be in there. We're going to have another S room that's slightly bigger, or orbital, and there's going to be 2 electrons around there. And then the P kinds of rooms where I have 4 electrons. One of the p orbitals looks like this, one of the p orbitals looks like this, one of the p orbitals look like this. And so I would have 1 electron chilling here in one of these, 1 electron chilling here in one of these, 1 electron chilling here in one of these, and then this is 2p4, so I have 1 more, so it's going to start doubling up. So really I have 2 here. And so these orbitals are the likely places these electrons are going to be, and so there we go. You do not need to memorize how these orbitals look like. You just have to know that they look different, like each of the rooms can look different. And again, they will fill up singly first before they start doubling up. And again, this is likely where the electrons are going to be around the nucleus. So again, here, S, we're assuming that the nucleus is at the point of XYZ. You have to think of this as a 3D kind of thing. And so that's why there's different colors and stuff. So like this P room, for example, is on the X-axis, and they're kind of like elliptical spheres around where it touches that nucleus, and then you got the rooms, and so those electrons could be chilling anywhere, and then they get weirder and weirder as you go through the D and the F orbitals. So again, It doesn't need to be perfect. You don't need to know all these, but you should know again that they have weird shapes and that they're going to single fill out before double filled out. And then these are the likelihood places the electrons are going to be at. You can see here, if I have like 8 electrons, right? So that would be oxygen as an example. You can see the S overlaps the P orbitals because again the nucleus is here, and so if I put all these things on top of each other, the S electrons versus the P electrons might actually hit each other. And then you could see it gets more and more complicated as I go from D and F. So it's not this perfect like circle thing where the electrons are chilling in an energy level. It is based off these weird orbital shapes. You'll learn more about this if you take certain upper division chemistry courses. Really depends on your major, so I'm not going to say you will run into this again. It really depends. Again, you don't need to do the quantum numbers. The quantum numbers would just tell you which electron and which orbital and stuff it's in. Here's a few examples of like, why the heck should I learn this? I'm not going to hardcore go into why, because you don't need to know that for the AP Chem test. But again, it tells you where the electrons are, and if you know where the electrons are, you can excite them to other energy levels and other orbitals. And so the reason why you need to know which electrons are going to be excited to move them to other orbitals is because of functionality, like lasers, for example, or detectors, or spectrometry, or predicting reactions. So you'll learn why electron configuration is a thing, again, depending on what courses you take in college. A lot of it is interesting, like in terms of predicting reactions, because then you can see what compounds are formed and all that stuff. It's actually really interesting in research purposes. Here's another way to memorize the SPDF stuff. So it makes something called the Christmas tree method. And so you go through 1S, and then you go through 2S, and then you go to 2P, and then 3S, and then 3P, 4S, and then 3D, 4P, 5S. And it goes in the order that you're filling it in. Transition metals, why they're +1 or +2. In terms of talking about them, it literally is just based off which ones you're going to remove. Usually it's the valence ones. Sometimes you're removing stuff from other places if you're going to be able to have all your rooms half filled out. So like the transition metals in the 3D, for example, sometimes you might not remove the valence electrons, because if you remove some from the D orbitals, for example, you might end up being half filled in the D orbitals, and then it actually is very stable. But again, those are those weird exceptions that I'm not going to hardcore talk about. But yeah, why transition metals have like certain charges is based off whether or not you're removing stuff from the valence or if you're removing stuff from the d orbitals. Okay, not related to electron configuration or that kind of stuff, but is important for 1.5 is Coulomb's law. Coulomb's law is a very, very common reason for FRQ answers. So trying to understand Coulomb's law, very beneficial to you. So Coulomb's law is talking about the electrical force between the two charged particles. And so when I think about helium, for example, I think about how the 2 protons in the middle are holding together the 2 electrons. It's that attraction between those charges. Now, I don't have to necessarily talk about attraction with Coulomb's law because it says electrical force between 2 charged particles. I could talk about, for example, the 1 proton and the 2nd proton in helium and how they would be repulsed by each other. So electrical force could be talking about attraction, or it could be talking about repulsion. So this is not on the constant equation sheet, as I said here. You need to memorize this in general and why we use it. The key thing is the why. Not necessarily like you just happen to know this like thing, but it's mainly the why. And so so F is going to be the force, the electrical force. Then Q is going to be the electrical charge of whatever we're talking about. And then R is the distance between whatever things we're comparing to. And so When I'm looking at this is a proportionality thing. And so we need to think about how the charges relate to the force, or how the charges relate to the distance, or how the distance relates to the force. Like, any of these could be related in some way. And so we have to think about why. And if you're like, what? It's a lot easier with an example. So I'm going to talk about those relationships shortly. So again, the force can be attraction or repulsion, as I said earlier. And so we're going to talk about this again in a future unit, but I'm going to again talk about it in terms of here. So we have the positive proton, most likely, yeah. And then we have the negative electron. So in this case, we're going to have an attractive force between the positive and the negative. So we're going to have an attraction here. A positive and a positive, they are not attracted to each other. They're repulsing most likely. Not always, but most likely. Because if you think about the nucleus, we have a whole bunch of protons in there, but that doesn't mean that they're always going to be, repulsing off each other, because the nucleus wants to stay together. One of the reasons we have neutrons is because of that. And then we have our negative charges, that's our electrons, and if I have two electrons near each other, they are repulsed too. Okay, so let's talk about the, how this works in terms of like a problem, because again, it's kind of confusing until you think about what I said earlier. So these are the stuff I said earlier. So let's think of an example. So if I think of sodium, which is here, and then I think of magnesium, which is here, I think about the increasing nucleus. So remember that sodium, again, atomic number is 11, so that it has 11 protons. For magnesium, it's going to be 12 protons. And so if I think about the Q value in terms of like neutral atoms of these guys, the sodium is going to have 11 protons, 11 electrons. So 11 times 11, that's like 21. And then magnesium, I have 12 protons, 12 electrons. Again, I'm just assuming neutrality. And so 12 times 12 is 144. So 121 versus 124, well, 124 is bigger. There's going to be a bigger attraction between something that has more protons versus less protons. And so when I increase that nucleus's proton amount, that's going to increase the attraction between the protons and the electrons. And so that's one of the relationships you should be able to figure out, again, just based off looking at this and then just thinking about numbers and how things would be attracted. Now, because magnesium, again, has more protons, even though it has more electrons too, more protons and electrons means more attraction towards each other, that attractive force is going to bring those electrons slightly closer together compared to the sodium one. And so because they're going to be closer together, this distance is going to be smaller between magnesium and its electrons versus sodium and its electrons. And again, we'll talk about this more when we talk about periodic trends, because this is a very, again, important concept based off attractions and distance and all that stuff. Okay, so your turn is on your paper. You're going to think about Coulomb's law. And then justify your answer on why 1 is 1. So number 1, you're either doing stronger or weaker. Number 2, da-da-da, and then da-da-da. And then number 3, there. So do this example. Again, try your best, because Coulomb's law is kind of confusing initially, and then it gets easier and easier as you apply it more. So look at each scenario, look at the equation, determine word choice. And then I'll talk about it in a few moments. So pause the video. Okay, so, boom. If you want me to explain any of these, please ask me in class or in our server, and then I will gladly explain these. But here are our answers. Ta-da! Last thing about this section is electrons as waves and particles. So one thing that's weird about electrons is they're technically quantum objects, which means that they act like both waves and particles at the same time. Now, traditionally, a wave is something we'll talk about more in the next section, but they have certain properties about them. Same with particles, we define them as certain properties. But electrons are weird. They're this kind of duality of being both a wave and both a particle, but also neither being a wave or neither being a particle. AP Chem does not focus on this really, but it is something that is interesting. And so if you're interested in that, if you go on the slides, I have this link that talks about it more. You'll learn more about this weird duality if you take future upper div chemistry, like quantum mechanics, for example. All right, that's it for section 1.5. Alrighty, bye.